Picture this: a single speck of dust floating in an endless ocean of darkness, a tiny fragment in a cosmos so vast that even light takes billions of years to cross it. That speck is our home, the Milky Way, just one among trillions of galaxies stretching farther than our minds can grasp. And here's the most astonishing part: that ocean isn't just vast, it's growing. Every second, the universe stretches a little wider, pushing galaxies apart in a silent, relentless expansion that defies everything we thought we knew. What's driving this cosmic runaway? Why is space itself stretching faster and faster, as if some invisible hand is tugging at the fabric of reality? The answers, or at least the wild, mind-bending theories scientists have dared to propose, will challenge everything you believe about existence. From the moment Edwin Hubble first noticed galaxies racing away from us, humanity has been obsessed with unraveling this mystery. But the deeper we dig, the stranger it gets. Dark energy, phantom universes, higher dimensions lurking just beyond our perception, theories so bizarre they sound like science fiction. Yet they're the best explanations we have for why the cosmos refuses to sit still. Some scientists argue we're living inside a black hole. Others whisper about parallel realities brushing against ours, their gravity warping our universe from the outside. And then there's the chilling possibility that we're simply wrong about everything, that gravity, time, even the laws of physics themselves might be illusions in a game we don't yet understand. This isn't just about distant stars or abstract equations, it's about the very nature of reality. If the universe is expanding, where does it end? Does it end? Could there be other expansions happening beyond our cosmic horizon, other bubbles of space and time blossoming in the dark? Over the next 30 theories, we'll venture into the bleeding edge of cosmology, where genius and madness blur, and where every answer leads to a dozen new questions. Buckle up, we're about to dive into the greatest mystery of all, the infinite, accelerating heartbeat of the cosmos itself. And trust me, by the end, you'll never look at the night sky the same way again. Let's rewind the cosmic clock back to the very beginning, or at least as close to it as we can get. The Big Bang wasn't an explosion in space, it was the explosive birth of space itself. Picture a single, unimaginably dense point, hotter and more packed with energy than anything that exists today. Then, in a fraction of a second, it erupted outward, stretching the fabric of reality like a balloon inflating faster than light. This wasn't just the start of matter and time, it was the first domino in a chain reaction that's still playing out 14 billion years later. But how do we know this actually happened? The clues are etched into the cosmos itself. Take the cosmic microwave background radiation, the faint afterglow of that primordial fireball. It's everywhere, a whisper of heat left over from when the universe was just 380,000 years old, finally cool enough for light to break free. That glow isn't random, it's a snapshot of the infant universe, riddled with tiny fluctuations that would one day grow into galaxies. Then there's redshift, the telltale sign that galaxies are racing away from us. The farther they are, the faster they recede, their light stretched into longer, redder wavelengths like a cosmic Doppler effect. It's as if the universe itself is a loaf of raisin bread baking, with every raisin, every galaxy moving apart as the dough expands. Yet here's the twist: the Big Bang didn't just give the universe a starting push. It baked something unexpected into the recipe, a force we still don't fully understand. Instead of slowing down as gravity pulled matter together, the expansion sped up. It's like tossing a ball in the air only to watch it shoot faster into the sky, defying every law of common sense. That's the mystery we're left with, a universe that began with a bang but seems determined to keep accelerating into the unknown, dragging us along for the ride. Now, imagine that initial expansion wasn't just fast, it was unimaginably faster than anything we see today. For a fraction of a second, smaller than the blink of an eye, the universe didn't just grow, it exploded in size, doubling and redoubling itself faster than light itself could keep up. This is cosmic inflation, the theory that rewrote our understanding of the Big Bang's first moments. Proposed by physicist Alan Guth in the 1980s, inflation solves mysteries so deep they once seemed unsolvable. Take the cosmic microwave background, that ancient afterglow we mentioned earlier. No matter which direction we look, its temperature is almost perfectly uniform, just a few tiny variations sprinkled across the sky. But here's the puzzle: without inflation, those distant regions of space could never have reached the same temperature. They were too far apart for heat to travel between them, even over billions of years. It's like two cups of coffee placed on opposite ends of a football field, somehow cooling to the exact same temperature without ever touching. Inflation fixes this by suggesting the entire visible universe was once crammed into a space tinier than a single atom, where everything was in intimate contact before being stretched apart in that sudden, exponential expansion. But inflation doesn't just explain uniformity, it also tells us why the universe isn't riddled with bizarre relics like magnetic monopoles, particles predicted by older theories but never observed. Inflation would have diluted these oddities to near non-existence, sweeping them away like cosmic clutter. And perhaps most stunning of all, it gives us a clue about why the universe seems so perfectly balanced between expansion and gravity. Without that delicate equilibrium, galaxies could never have formed. Inflation fine-tuned the cosmos in its first moments, leaving behind a universe poised between chaos and collapse. Yet for all its successes, inflation remains a theory, one with competing versions and unanswered questions. Some scientists argue it's too flexible, able to explain almost any observation after the fact. Others wonder what triggered that sudden expansion, or whether multiple episodes of inflation could have created a multiverse, with countless bubble universes blooming in an endless cosmic froth. What we do know is this: inflation reshaped not just the early universe, but our very approach to cosmology. It's a reminder that sometimes the wildest ideas, the ones that defy common sense, hold the keys to reality's deepest secrets. Now, let's shine a light on the shadowy force that's pulling the universe apart at the seams: dark energy. Picture gravity as the cosmic glue that should be slowing everything down, pulling galaxies together like marbles on a rubber sheet. But in the late 1990s, two teams of astronomers made a discovery that turned this assumption on its head. By observing distant supernova exploding stars that serve as cosmic mile markers, they found something impossible. The universe wasn't just expanding, it was accelerating. It was as if someone had flipped a switch, turning gravity's pull into an invisible push. This repulsive force, dubbed dark energy, makes up roughly 68% of everything in existence. Yet we know almost nothing about it. Unlike matter or radiation, dark energy appears to be woven into the fabric of space itself, a property of empty nothingness that generates more emptiness. Einstein actually predicted something similar with his cosmological constant, a mathematical fudge factor he later called his biggest blunder. Little did he know, his equations might have been right all along. Here's why dark energy bends the mind: it acts like anti-gravity. While matter and energy curve space-time inward, dark energy stretches it outward, creating more space where none existed before. And because this energy is tied to space itself, the more the universe expands, the more dark energy there is to fuel further expansion. It's a runaway feedback loop with no end in sight, a cosmic hall of mirrors where distances grow exponentially, isolating galaxies in vast voids of darkness. But the biggest puzzle: we can't see it, touch it, or detect it directly. Dark energy reveals itself only through its gravitational footprint, its presence inferred from the way galaxies flee from one another. Some theories suggest it's a new kind of field, like the Higgs field, but with bizarre repulsive properties. others propose it's evidence of extra dimensions leaking into our reality. Or perhaps our understanding of gravity itself is incomplete, and Einstein's theory needs rewriting on cosmic scales. One terrifying possibility is that dark energy's strength could change over time. Right now, it's relatively weak, just strong enough to drive galaxies apart but not rip apart planets or atoms. But if it were to intensify, that could lead to the Big Rip, a scenario where the cosmos tears itself to shreds, from galaxy clusters down to subatomic particles. Alternatively, dark energy might fade away, allowing gravity to regain control and pull everything back in a cosmic reversal of the Big Bang. The truth is, dark energy remains the greatest unsolved mystery in cosmology. It's the ghost in the cosmic machine, the unseen hand shaping the fate of everything. And until we crack its code, the universe will keep accelerating into the unknown, carrying us along for the ride. Einstein's biggest blunder might have been his greatest accidental prophecy. When he first scribbled down the equations of general relativity, they told him something unsettling. The universe should either be collapsing under its own gravity or flying apart. But in the early 20th century, astronomers believed the cosmos was static, eternal, and unchanging. To force his theory into alignment with that belief, Einstein tacked on a fudge factor, a mathematical placeholder he called the cosmological constant. It represented a repulsive force, subtle but pervasive, woven into the fabric of space itself to balance gravity's pull and keep the universe perfectly still. Then came Edwin Hubble's bombshell discovery: the universe wasn't static at all. Galaxies were racing away from each other, evidence of an expanding cosmos. Einstein, convinced he'd been wrong, famously dismissed the cosmological constant as his greatest mistake. But here's the twist: decades later, when astronomers found the universe's expansion was accelerating, they realized Einstein's discarded idea might hold the key after all. That arbitrary constant, it behaves exactly like the mysterious dark energy pushing galaxies apart today. The cosmological constant suggests empty space isn't really empty. Quantum physics tells us that even a perfect vacuum crackles with virtual particles, pairs of matter and antimatter flickering in and out of existence. This quantum foam might generate a tiny, constant energy density that stretches space-time itself. If true, dark energy isn't some exotic substance but an intrinsic property of the universe, as fundamental as the speed of light. Yet problems linger. When physicists calculate how much energy this quantum foam should produce, the numbers are absurdly off by a factor of 10 followed by 120 zeros. That's the worst prediction in the history of science, a discrepancy so colossal it's called the vacuum catastrophe. Some argue it means we're missing a deeper symmetry in nature, a hidden law that cancels out this energy. Others think the cosmological constant is just a placeholder for something far stranger, a dynamic field that evolves over time, or evidence of unseen dimensions leaking into our reality. Despite these flaws, the cosmological constant remains a leading contender because it's simple and fits the data eerily well. It requires no new particles or forces, just a slight tweak to Einstein's original equations. But simplicity doesn't always mean truth. If the constant is real, why is its value so perfectly tuned to allow galaxies and life to exist a fraction larger, and the universe would have torn itself apart before stars could form? A fraction smaller, and gravity would have crushed everything back into a singularity. That fine-tuning hints at either staggering cosmic luck or something we haven't yet imagined. Einstein may have hated his own idea, but its revival proves even geniuses can't always see the future hiding in their mistakes. What if dark energy isn't constant at all? What if it ebbs and flows like a cosmic tide, growing stronger or weaker as the universe ages? This is the tantalizing idea behind quintessence, a theory that shakes up everything we thought we knew about the universe's expansion. Unlike the rigid, unchanging cosmological constant, quintessence imagines dark energy as a dynamic force field, one that could evolve over billions of years or even flicker out entirely. Think of it like this: the cosmological constant is a steady hand holding a stretched rubber sheet taut, never loosening its grip. Quintessence, though, is more like a living thing, breathing, shifting, sometimes pressing harder and other times relaxing. It's named after the ancient Greek fifth element, the mysterious substance believed to permeate the heavens. And just like that ancient concept, modern quintessence is elusive, its behavior governed by an unknown energy field that fills space but doesn't behave like matter or radiation. Here's where it gets fascinating. If quintessence is real, it could solve one of cosmology's biggest headaches, the staggering fine-tuning problem. The cosmological constant's value is so bizarrely precise that even a slight change would have prevented galaxies or even atoms from forming. Quintessence offers a way out. Instead of being locked in from the Big Bang, this field could have started weak and grown stronger over time, adjusting itself naturally to allow life to emerge. It's as if the universe has a dimmer switch, subtly turning up the brightness of expansion only after stars and planets had their chance to exist. But how would we spot such a shadowy, shifting force? The key lies in watching how the universe's expansion changes across cosmic time. Right now, telescopes like the James Webb Space peering deep into the past, they're measuring the brightness of ancient supernova and the clustering of galaxies, hunting for subtle deviations from the predictions of a constant dark energy. If quintessence is at work, these observations might reveal moments when the universe's acceleration sped up or slowed down, clues etched into the light of dying stars billions of years ago. Yet quintessence isn't without its own mysteries. Some models suggest it could eventually reverse course, turning from a repulsive force into an attractive one, pulling the universe back into a catastrophic big crunch. Others speculate it might one day surge violently, tearing apart galaxies in a future big rip. And then there's the unsettling possibility that we're seeing just one phase of a cycle, an expansion today, a contraction tomorrow in an endless cosmic heartbeat. The stakes couldn't be higher. If quintessence is real, it would rewrite our understanding of physics, revealing a universe far more dynamic and unpredictable than Einstein ever imagined. But if it's just a mirage, we're back to wrestling with that infamous cosmological constant and its impossible fine-tuning. For now, quintessence remains a ghost in the equations, a maybe hiding in the data. And that's what makes it so thrilling. It's not just another theory, but a dare, a challenge to look deeper, to question every assumption, and to remember that the universe, in all its vastness, might still be holding its greatest secrets close. One of the most terrifying possibilities lurking in the shadows of cosmic expansion is the Big Rip, a scenario so violent it makes black holes look merciful. Imagine dark energy isn't just a constant force, but one that grows stronger over time, like a spring coiling tighter and tighter until it snaps. At first, galaxies would drift apart, their gravitational bonds no match for the mounting pressure. Then, as the force intensifies, star systems would unravel, planets torn from their suns like beads scattered from a broken necklace, but the horror wouldn't stop there. In the final moments, even atoms, the building blocks of reality itself, would be wrenched apart, their protons and electrons ripped away in a universe where not even the fabric of matter could hold. Timing is everything in this cosmic demolition. If the Big Rip is real, calculations suggest it could happen in as little as 22 billion years, a blink on the universe's timescale. First, galaxy clusters would lose their grip on one another around 60 million years before doomsday. 9 months before the end, solar systems would disintegrate. 30 minutes before annihilation, stars and planets would explode from within. And in the last fraction of a second, spacetime itself would shatter, leaving behind a cold, empty void where the laws of physics no longer apply. What makes this scenario so chilling isn't just the destruction, but the inevitability. Unlike black holes or supernova, there's no escape from a big rip, no bunker deep enough, no technology advanced enough to outrun the stretching of space itself. Even time would lose all meaning as the universe's final moments stretch into an infinite, agonizing instant. Some theories suggest remnants of matter might survive in isolated bubbles like shipwrecks in an endless ocean of nothingness. But most likely, the Big Rip would erase every trace of existence, leaving no memory that anything had ever been here at all. Yet for all its drama, the Big Rip isn't guaranteed. Its likelihood hinges on a property of dark energy called its equation of state, a measure of how its pressure relates to its density. If this value dips below a critical threshold, the universe's fate is sealed. Current observations leave the door open, but only slightly. That uncertainty is what keeps cosmologists awake at night. Because if dark energy is even slightly more sinister than we've measured, the cosmos isn't just expanding, it's on borrowed time. While the Big Rip paints a picture of the universe tearing itself apart, there's an equally dramatic but opposite fate lurking in the equations of cosmology, the Big Crunch. Imagine the expansion of the universe slowing, halting, then reversing like a cosmic inhale, drawing all matter and energy back into a single, searing point. Galaxies would rush toward each other, their light blue shifting as space contracts. Stars would collide, black holes merge, and the temperature of the universe would soar until even atoms themselves disintegrate in the heat. This isn't just an ending, it's a cosmic reset button, a collapse so total it might birth a new universe from the ashes. The idea hinges on a simple question: what if dark energy isn't permanent? If its repulsive force weakens over time, gravity could regain dominance. Like a ball thrown upward that eventually slows and falls back to Earth, the universe's expansion might reverse. Some versions of quintessence even suggest this field could flip from repulsive to attractive, pulling everything inward. The result wouldn't be a slow decline, but an accelerating collapse, a mirror image of the Big Bang running in reverse. But here's where it gets stranger. Some theories propose the Big Crunch might not be the end at all. Instead, it could trigger a big bounce, where the collapsing universe rebounds into a new expansion phase. Quantum physics suggests that at incredibly high densities, space itself might resist total collapse like a spring compressed to its limit. This opens the door to cyclic models, where universes expand, contract, and rebirth in an endless loop. Each cycle could last trillions of years, with subtle variations in the laws of physics each time, creating a multiverse of trial and error cosmoses. Evidence for this idea is thin but tantalizing. The cosmic microwave background shows slight anomalies, unexplained, cold spots, and asymmetries that some argue could be echoes of a pre-Big Bang universe. And certain quantum gravity models predict that a collapsing universe wouldn't reach infinite density, but instead bounce at a Planck-scale minimum size. It's a poetic vision, death and rebirth woven into the fabric of spacetime itself. Yet the Big Crunch faces its own challenges. Current measurements suggest dark energy's strength is holding steady, not fading. And even if collapse were inevitable, the universe's sheer size means it would take longer than its current age just for the stop expanding signal to reach distant galaxies. Still, the possibility lingers, a reminder that the cosmos might not be on a one-way trip to oblivion, but part of a grander, unseen rhythm. Whether it ends in fire, ice, or rebirth, the universe's fate remains the ultimate cliffhanger. The Big Freeze is a cosmic fate so desolate it makes black holes seem warm by comparison. Imagine a universe where expansion never stops, where galaxies drift apart like lonely ships in an endless dark sea until each one is utterly isolated. Stars, those brilliant beacons of light, would exhaust their fuel one by one, red giants fading to white dwarfs, massive stars collapsing into neutron stars or black holes, their last gasps of energy swallowed by the void. Over trillions of years, even the smallest red dwarfs, stars that burn for longer than the current age of the universe, would finally flicker out. The cosmos, once ablaze with light and heat, would cool to near absolute zero, a vast graveyard of dead stars and frozen planets. This is heat death, not a fiery cataclysm, but a slow, inevitable fade into maximum entropy, the point where no energy can be extracted from the universe because everything has reached equilibrium. It's the ultimate triumph of disorder over structure, where even black holes, the last bastions of concentrated energy, would eventually evaporate via Hawking radiation, leaking particles into the darkness until nothing remains but a thin, uniform haze of subatomic particles drifting forever apart. Time itself would lose all meaning, with no processes left to measure it, no events to mark its passage. The universe would become a static, featureless expanse, frozen in a state of perfect and perfectly lifeless balance. What makes this scenario so unsettling isn't just the absence of light or heat, but the irreversible erasure of complexity. Life, planets, even the atoms that make them up, rely on energy differences: hot and cold, high pressure and low, order and chaos. In a heat-dead universe, those gradients vanish. No stars mean no new heavy elements, no planets, no chemistry. Atomic nuclei themselves might decay over incomprehensible timescales, leaving behind only photons and leptons too dispersed to interact. It's a future where nothing happens forever. Yet there's a haunting beauty in this bleak vision. The big freeze isn't violent or sudden. It's the universe exhaling slowly, settling into stillness like a clock winding down. Some theories even suggest pockets of low entropy order could survive unpredictably, like eddies in a stagnant river. But for all practical purposes, heat death is the end of history, not with a bang, but with an infinite, unbroken silence. The chilling takeaway: if dark energy keeps accelerating expansion, this isn't just a possibility. It's the default future, written into the laws of thermodynamics themselves. What if our universe isn't the only one out there? What if the endless expansion we're witnessing isn't just stretching space, it's creating entirely new universes, each with its own laws of physics, its own version of reality? This is the mind-bending premise of the multiverse theory, where our cosmos is just one bubble in an infinite froth of universes, each born from the same chaotic process that sparked our own. Picture eternal inflation, the idea that the exponential expansion of the early universe never truly stopped. Instead, it continues in distant regions of space, where quantum fluctuations keep triggering new bursts of inflation, each one birthing a fresh universe like ours. Think of it as a cosmic version of a boiling pot of water. Bubbles form, expand, and detach, each one a self-contained realm with its own unique properties. Some might have stronger gravity, others might lack dark energy entirely, and a few could even harbor dimensions we can't begin to imagine. The implications are staggering. If eternal inflation is real, then the multiverse isn't just a hypothetical playground, it's an inevitable consequence of the physics driving our universe's expansion. And here's where it gets even wilder. These bubble universes wouldn't just sit idly in some higher dimensional void. They could collide, merge, or even leave scars on each other. Some scientists speculate that faint irregularities in the cosmic microwave background, those enigmatic cold spots, might be bruises from long-ago collisions with other universes, like fingerprints pressed against the glass of spacetime. But how could we ever prove something so extraordinary? Direct observation is nearly impossible. These other universes would lie beyond our cosmic horizon, forever out of reach. Yet there are indirect clues. If inflation is eternal, then certain statistical patterns in our universe's structure should align with the predictions of multiverse models. Others hunt for gravitational waves from the Big Bang, which could carry echoes of primordial bubble formations. And then there's the haunting possibility that the laws of physics in our universe aren't fundamental at all, just a random draw from a cosmic lottery, one ticket among infinite others. The multiverse theory doesn't just reshape our understanding of space, it rewrites the meaning of existence itself. If countless universes exist, then every possible outcome, every alternate history, every variation of reality might be playing out somewhere in the infinite expanse. It's a humbling thought. Our entire cosmos, with its billions of galaxies and trillions of stars, might be nothing more than a speck in an unfathomably vast meta-universe where beginnings and endings are happening all the time, just beyond the edge of perception. The holographic principle flips our understanding of reality inside out. What if everything we see, from swirling galaxies to the vast cosmic expansion itself, is just a shadow cast by a two-dimensional surface at the edge of the universe? It sounds like science fiction, but this radical idea emerges from the deepest puzzles of black holes and string theory. Picture a hologram, a flat, patterned surface that creates the illusion of three dimensions when light hits it just right. Now imagine the entire cosmos working the same way, with every event, every particle, even the fabric of spacetime itself, encoded on a distant, invisible boundary like data on a cosmic hard drive. This isn't just philosophical musing, it's grounded in hard physics. The spark came from studying black holes, those cosmic traps where gravity is so strong nothing escapes, not even light. In the 1970s, Jacob Bekenstein and Stephen Hawking made a startling discovery. A black hole's entropy, a measure of its hidden information, is proportional not to its volume, but to the area of its event horizon, the point of no return. It's as if all the matter swallowed by the black hole gets compressed into a flat, two-dimensional surface, with the third dimension an illusion. This led theoretical physicist Gerard T. Hooft to propose that the universe might work the same way, a three-dimensional reality projected from information stored on a two-dimensional boundary at infinity. String theory takes this even further. In some versions of the theory, the equations describing our universe only work if we assume it's a hologram, a projection from a lower dimensional space where gravity doesn't even exist. It's like discovering the movie you've been watching your whole life is actually being played from a DVD you never knew existed. The implications for cosmic expansion are staggering. If the holographic principle is true, then dark energy and the accelerating universe might not be features of our 3D world at all, but artifacts of whatever's happening on that distant 2D surface. The expansion we measure could be a side effect of information processing in a realm we can't see or touch. Critics argue the holographic principle is untestable, a beautiful idea with no way to verify it. But supporters point to subtle clues. The way quantum entanglement spooky action at a distance mirrors the connections between points on a hologram surface, or how certain calculations about particle collisions only make sense if we assume the universe has fewer true dimensions than it appears. If they're right, then the greatest mystery of cosmology, why space keeps stretching, might not be about space itself, but about something far stranger. A flat, hidden canvas where reality is being painted, stroke by stroke, into the illusion of depth we call home. Einstein's famous constant, the speed of light, is etched into the foundation of modern physics as an unbreakable cosmic speed limit. But what if it wasn't always so constant? What if, in the searing heat of the early universe, light raced across space faster than it does today? This is the radical premise of variable speed of light theories, where the very rules of reality might have shifted during the universe's infancy, dramatically reshaping how we understand cosmic expansion. The idea first gained traction as a potential solution to one of cosmology's stickiest puzzles, the horizon problem. We've already seen how the cosmic microwave background is eerily uniform across the sky, yet regions far apart couldn't have exchanged heat or information unless something allowed them to communicate faster than light. Inflation solves this by stretching space itself, but variable light speed offers an alternative. If photons traveled unimaginably faster in the first moments after the Big Bang, distant regions could have thermalized before the cosmic brakes kicked in, locking light into its current, slower pace. Proponents like physicist Joe Megiddo argue this isn't just mathematical hand-waving. Some models suggest light speed could have been up to 60 orders of magnitude faster in the early universe, enough to explain uniformity without invoking inflation's exponential growth spurt. Even more provocatively, these theories predict subtle fingerprints in the cosmic microwave background, specific patterns in the polarization of ancient light that telescopes like Planck have hunted for. Preliminary studies have hinted at anomalies, slight deviations from what standard cosmology predicts, though nothing conclusive yet. Critics, however, aren't convinced. Altering light speed unravels a thread that could unravel all of physics. Einstein's relativity is built on the constancy of c. Change that, and everything from particle physics to gravity gets thrown into chaos. Energy conservation, causality, even the structure of spacetime itself would need radical reworking. And then there's Occam's razor. Why introduce a variable speed of light when inflation already explains the observation so elegantly? Yet the debate is far from settled. Some versions of string theory and quantum gravity actually require dimensional constants like c to fluctuate at ultra-high energies. Others suggest light speed might vary not just over time, but across space, creating pockets of reality where physics operates differently. And if future telescopes do confirm those telltale patterns in the microwave background, we might be forced to rewrite the textbooks. After all, constants are only constant until they're not. The universe, it seems, loves keeping us guessing. What if dark energy is just a cosmic mirage, an illusion created because we've been measuring gravity wrong all along? That's the bold claim of modified Newtonian dynamics, or MUND, a theory that throws out the need for invisible forces by rewriting the rules of gravity itself. Picture this: for centuries, we've assumed Isaac Newton's law of gravity works the same everywhere, from apples falling on Earth to galaxies orbiting in deep space. But when astronomers observed stars whirling around galactic edges faster than Newton's equations predicted, they invented dark matter to explain the discrepancy. Then, when the universe's expansion accelerated, they conjured dark energy. MUND says enough. What if gravity simply behaves differently where the pull is incredibly faint? At the heart of MUND is a startling idea. Gravity doesn't fade smoothly with distance as Newton and Einstein assumed. Instead, below a certain threshold about 10 billion times weaker than Earth's gravity, it transitions to a different set of rules. In this regime, the force weakens less sharply, giving distant stars an extra tug that mimics the effect of dark matter. It's like discovering water flows uphill under certain conditions, not because of some hidden pump, but because we misunderstood fluid dynamics. Proponents argue MUND neatly explains galactic rotation curves without invoking unseen particles, matching observations with eerie precision in over 100 galaxies. But cosmic expansion is where MUND faces its toughest test. If dark energy doesn't exist, why is the universe accelerating? Some modified gravity theories propose tweaks to Einstein's relativity on colossal scales, suggesting spacetime reacts differently to vast cosmic voids than to galaxy clusters. Imagine pushing a shopping cart normally. It moves predictably, but on an unseen slope, it might roll unexpectedly. Similarly, gravity in a near-empty universe could have a repulsive effect, mimicking dark energy's push without any mysterious substance. Critics, though, aren't swayed. MUND struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate visible matter from gravitational effects, exactly what dark matter predicts. And while MUND excels at galactic scales, it falters when applied to the universe as a whole. Yet the theory refuses to die, evolving into more sophisticated versions like tensor vector scalar gravity (TVS), which attempts to reconcile MUND with relativity. The stakes couldn't be higher. If MUND is right, we're on the verge of overturning centuries of physics. If it's wrong, its persistence highlights how desperately cosmology needs answers beyond invisible stuff we can't detect. Either way, Mund forces us to ask, are we missing a cosmic cheat code, a hidden adjustment to gravity's settings that would make everything click into place? Until we know, the universe keeps its secrets written either in Dark Energy's phantom ink or in the fine print of gravity's rulebook we've yet to fully read. Phantom energy isn't just another form of dark energy, it's dark energy on steroids, a hypothetical substance so destructive it makes the Big Rip look like a gentle exhale. Imagine a force that doesn't just accelerate cosmic expansion, but does so with such ferocity that space-time itself loses all cohesion. Galaxies wouldn't merely drift apart, they'd be violently shredded, atom from atom, long before the universe's natural lifespan expires. Stars, planets, even the very fabric of matter would dissolve into a chaotic sea of disconnected particles, erased from existence in a cosmic instant. This nightmare scenario hinges on a single, terrifying property. Phantom energy's density increases over time. Unlike the cosmological constant, which stays steady, or quintessence, which might fade, phantom energy grows stronger as space expands, creating a feedback loop of self-destruction. Picture stretching a rubber band until it snaps, except the rubber band is reality itself, and every stretch makes the material weaker, not stronger. Theoretical models suggest that if phantom energy exists, it could reduce the universe's lifespan from trillions of years to as little as 20 billion, a blink in cosmic terms, leaving no time for life to re-emerge in distant epochs. Where does such a radical idea come from? The math traces back to certain solutions of Einstein's equations where the equation of state of dark energy, the ratio of its pressure to density, dips below -1. In everyday physics, this is impossible. It implies a substance that defies fundamental energy conditions. But in the quantum realm, where virtual particles borrow energy from nothingness, some theorists argue phantom energy might lurk as a fluke of particle physics gone wrong. Others tie it to string theory's landscape of vacuum states, where our universe might sit perched on an unstable energy slope, destined to crumble into a lower energy state with catastrophic consequences. Yet for all its mathematical intrigue, phantom energy remains fringe science, and for good reason. No observational evidence supports it, and its existence would violate cherished principles like the null energy condition, which prevents matter from behaving in ways that break causality. Plus, if phantom energy were real, we'd likely see its fingerprints already. Galaxies at the edge of our observable universe should show signs of being torn apart by unseen forces, their light stretched into unrecognizability. So far, the cosmos looks mercifully quiet on that front, but the real value of phantom energy lies in its warning. By exploring these extreme edges of theory, physicists test the limits of what the universe could do even if it never does. It's a reminder that the cosmic expansion we take for granted is far more fragile than it seems, balanced on a knife's edge between stability and oblivion. And perhaps that's the most unsettling thought of all. The forces shaping our universe's fate might not just be unknown, but unknowable, lurking in equations we haven't yet dared to write. What if our universe isn't the first or the last in an endless cycle of cosmic rebirth? The ekpyrotic universe theory dares to imagine exactly that, painting a picture where the Big Bang wasn't a one-time event, but the latest collision in an eternal dance between higher dimensional worlds. Picture two immense parallel sheets of reality called brains, short for membranes floating in a hidden higher dimensional space. These aren't just abstract ideas. In string theory, brains could be vast, dynamic surfaces where particles and forces are trapped, like ants crawling on a tablecloth. Now imagine these cosmic tablecloths drifting toward each other over eons, finally smashing together with enough energy to ignite a new universe. That catastrophic impact. That's our Big Bang, not an explosion from nothing, but a shockwave from a collision in a realm beyond our perception. This radical idea turns inflation on its head. Instead of a fleeting, exponential expansion, The Apocalyptic model suggests the universe began flat and smooth because those colliding branes were perfectly aligned, their energy distributed evenly across the crash site. No need for a hyper-fast stretching of space. The uniformity comes pre-packaged in the geometry of the collision itself. Even more intriguing, this theory predicts subtle differences in the cosmic microwave background, specific patterns of gravitational waves or temperature variations that inflation wouldn't produce. These fingerprints could one day be spotted by next-generation telescopes, offering hard evidence that our cosmos was born from a cosmic fender bender. But the wildest twist, the cycle doesn't end there. After the branes collide and rebound, they gradually drift apart, only to be pulled together again by invisible forces, setting the stage for another collision, another Big Bang, another universe. Time becomes a loop with no true beginning or end, just an infinite sequence of cosmic awakenings and quiet stretches between calamities. Some versions of the theory even suggest that each cycle might tweak the laws of physics slightly, creating variations in gravity, particle masses, or dark energy strength. It's a universe where the constants aren't constant at all, but temporary settings in an endless game of cosmic trial and error. Critics, though, point out glaring challenges. For one, the math requires branes to approach each other with near-perfect alignment, a fine-tuning problem rivaling even the cosmological constant's precision. And while the Apocalyptic model elegantly explains the universe's smoothness, it struggles with other observations, like the precise spectrum of temperature fluctuations in the cosmic microwave background. Then there's the elephant in the room. If we're living on a brane, why can't we detect the higher dimensional space around us? Supporters counter that gravity might leak into the extra dimensions, subtly altering its strength over vast distances, a ghostly hint of the unseen realms just beyond our grasp. Whether the Apocalyptic universe is poetry or physics remains to be seen, but its bold vision forces us to rethink the very nature of time, space, and existence. If true, our universe isn't a solitary accident, but one note in an infinite symphony of collisions, a cosmic heartbeat echoing across dimensions we may never see, but whose rhythm might yet be written in the oldest light bathing our sky. Entropy, the relentless force driving chaos and disorder, might hold the key to gravity itself, and rewrite our understanding of cosmic expansion in the process. This is the audacious claim of entropic gravity, a theory that flips conventional physics on its head by suggesting gravity isn't a fundamental force at all, but an emergent phenomenon, a side effect of the universe's innate tendency toward disorder. Picture a crowded room where every movement creates ripples of shifting space. According to physicist Eric Verland, gravity works the same way, arising from the natural shuffling of microscopic information on the edge of spacetime. Verland's theory builds on a radical idea first hinted at by black hole physics. Gravity might be entropy in disguise. Just as heat flows from hot to cold, gravitational attraction could emerge from systems seeking higher entropy states. Imagine spacetime as a frothing sea of invisible bits, quantum information constantly rearranging itself. When matter disturbs this sea, like a boulder dropped in a pond, the bits reorganize to maximize entropy, creating what we perceive as gravity's pull. It's as if the universe is playing a cosmic game of Tetris, where gravity is simply the tiles settling into place. Now apply this to dark energy. If gravity emerges from entropy gradients, then the accelerating expansion of space could reflect a deeper thermodynamic shift. As the universe grows, the sheer volume of empty space increases, altering how entropy is distributed. The result, a subtle pressure pushing galaxies apart, not from some mysterious dark energy, but from the universe's natural tendency to spread out information evenly. Verland's math suggests this cosmic thermal drift could mimic dark energy's effects without requiring any exotic substances, turning one of cosmology's biggest mysteries into a natural consequence of physics' most fundamental law. Critics, though, aren't ready to discard dark energy just yet. Entropic gravity struggles to explain certain galactic motions without tweaks, and it's yet to make testable predictions distinct from general relativity. But supporters point to tantalizing clues, like the way entropy-based models naturally align with observed galaxy rotation curves. No dark matter required. If Verland is right, we're not just redefining gravity, we're witnessing the birth of a new paradigm where the universe's expansion isn't driven by unseen forces, but by the silent, inexorable dance of chaos and order playing out on the quantum stage. The implications are staggering. Dark energy, black holes, even the nature of spacetime itself might all be shadows cast by a deeper, information-theoretic reality. It's a vision of the cosmos where the familiar laws of physics are just surface-level symptoms of something far stranger. A universe that isn't just expanding, but computing, rewriting its own rules one entropy gradient at a time. What if dark energy isn't a steady, unchanging force, but one that ebbs and flows like a cosmic tide? Time-varying dark energy proposes exactly this, a universe where the repulsive power driving galaxies apart isn't constant, but shifts over billions of years, sometimes surging, sometimes fading. Imagine turning a dimmer switch up and down on the cosmos itself, altering the speed of expansion not just once, but repeatedly across time. This wild idea could solve one of cosmology's greatest puzzles: why different methods of measuring the universe's expansion rate keep giving conflicting answers. The first clues emerged when astronomers noticed a nagging inconsistency. Distant supernova suggested a faster expansion rate than predictions based on the cosmic microwave background. It's like two clocks ticking at different speeds with no obvious reason why. If dark energy's strength has changed, though, that discrepancy starts to make sense. Early in cosmic history, a weaker dark energy might have allowed gravity to build galaxies and clusters, while a later surge could explain why the expansion now seems to be racing ahead. Some models even suggest dark energy could oscillate, swinging between stronger and weaker phases in a cycle stretching billions of years. Proving this, however, is fiendishly difficult. Dark energy's fingerprints are subtle, and teasing out variations requires painstaking observations across cosmic time. Projects like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies, hunting for minute shifts in their distribution that might reveal a changing repulsive force. Others study baryon acoustic oscillations, frozen echoes of primordial sound waves, to see if they've stretched differently in various eras. Even the James Webb Space Telescope is peering back to when the universe was half its current age, searching for supernova whose brightness could betray fluctuations in dark energy's push. Yet this theory isn't without controversy. Critics argue that adding variability introduces unnecessary complexity, like inventing a new gear to fix a watch that might just need winding. The cosmological constant simplicity is hard to abandon, and without definitive evidence, time-varying dark energy remains a tantalizing what if. But if future data confirms these ripples in cosmic acceleration, it would rewrite our understanding of the universe's fate. A dark energy that grows stronger could doom us to a big rip, while one that fades might let gravity claw back control, setting the stage for a big crunch. The most thrilling possibility: dark energy might not follow any predictable pattern at all. Like a capricious cosmic weather system, its strength could shift unpredictably, leaving us in a universe where the rules of expansion are written in sand, not stone. Until we know more, one thing's certain: the cosmos still has surprises up its sleeve. Here's an unsettling thought: what if our universe isn't expanding into an endless void, but is instead trapped inside the crushing depths of a black hole? At first glance, the idea sounds like science fiction, but when you peel back the layers, the math starts to whisper something eerie. Black holes, those cosmic monsters where gravity overwhelms all other forces, might not just be objects in the universe. They could contain universes of their own, with ours being one of them. Take a step back and consider the parallels. A black hole's event horizon, the point of no return, marks a boundary where space and time twist beyond recognition. But what happens to all that matter and energy swallowed by the singularity? Some theories suggest it doesn't just vanish. Instead, the extreme curvature of space-time inside could create the conditions for an entirely new cosmos, bubbling into existence like a hidden universe within a universe. The expansion we observe, that might just be the gravitational echo of the black hole's birth, stretching space from the inside out in a way that eerily resembles our own cosmic inflation. Even more mind-bending is the holographic principle. If a black hole's entropy is encoded on its two-dimensional surface rather than its three-dimensional volume, could our universe, with all its galaxies, stars, and planets, also be nothing more than a projection? It's like realizing the world around you is a shadow play cast from the walls of some unimaginable prison. The math even aligns. The equations describing a black hole's interior bear a striking resemblance to those governing our universe's expansion, as if both are playing by the same cosmic rulebook. Critics, of course, raise eyebrows. If we're inside a black hole, where's the crushing tidal force that should tear atoms apart? Proponents counter that the black hole hosting us might exist in a higher dimensional space where the forces balance differently. Others point out that the observable universe's mass and radius fit suspiciously well with the properties of a hypothetical black hole in a bulk universe beyond ours. Whether this theory holds water or not, it forces us to confront a humbling possibility that our entire cosmic neighborhood might be nested inside something far stranger, a Russian doll of realities where every layer defies comprehension. The universe as a black hole isn't just a wild guess, it's a mathematical dare, challenging us to rethink where we truly are in the grand scheme of existence. Cosmic strings sound like something ripped straight from the pages of a sci-fi novel, threads of pure energy thinner than an atom but stretching across the universe, carrying the mass of entire galaxies in their razor-thin cores. These bizarre relics, if they exist, are scars from the universe's violent infancy, when space-time itself underwent a phased transition like water freezing into ice. Just as ice crystals form cracks as they solidify, the cosmos might have developed defects, one-dimensional cracks in reality where the fabric of space-time didn't smooth out quite right. And these cracks could still be here today, invisible yet bending the universe around them with their unimaginable gravitational might. Picture a cosmic string as a flaw woven into the tapestry of reality, so dense that a single-inch-long segment would outweigh Mount Everest. Yet despite their mass, they'd be nearly undetectable unless you stumbled right into one. Their gravitational influence would be bizarrely localized, not a radial pull like a planet or star, but a sharp, lens-like distortion. Light passing near a string would split into double images as if the universe itself had a glitch. Even stranger, if a string brushed past Earth, we wouldn't feel a tremor. Instead, clocks in different cities might suddenly disagree, their ticks desynchronized by the string's warping of time itself. But how could these ghostly threads affect cosmic expansion? Here's where it gets fascinating. A network of cosmic strings could act like invisible puppet strings, tugging matter into denser filaments that shape the large-scale structure of the universe. Some theories suggest their immense tension might even contribute to dark energy's repulsive effect, adding another layer to the mystery of accelerating expansion. Others propose that strings could create knots in spacetime where gravity briefly overpowers expansion, forming exotic regions where galaxies cluster unnaturally tight. The hunt for these elusive objects is already underway. Astronomers scour the cosmos for telltale signs, sudden, unexplained shifts in the light of distant quasars, or peculiar voids in galaxy distributions where a string might have swept matter aside like a cosmic plow. Some even listen for the gravitational waves strings might emit if they snap or collide, rippling spacetime with pulses detectable by observatories like LIGO. Yet the most tantalizing possibility isn't just finding cosmic strings. It's what they'd reveal about the universe's first moments. Their existence would confirm that the early cosmos underwent symmetry-breaking phase transitions, freezing fundamental forces into their current forms. It's like discovering fossilized footprints in the quantum foam, proof of a time when reality itself was still setting its rules. Whether they're out there or not, cosmic strings remind us that the universe might be threaded with invisible scars, a hidden architecture written in gravity, time, and the echoes of creation. Imagine the universe as a frozen lake in midwinter, seemingly solid, stable, but hiding a deadly secret beneath the ice. What if the ground beneath our feet, the air we breathe, even the atoms that make up our bodies, are all perched on a fragile quantum ledge, one wobble away from total annihilation? This is the nightmare scenario of vacuum decay, where the very fabric of reality could unravel in an instant, rewriting the laws of physics in a shockwave that races across the cosmos at the speed of light. The danger lies in the Higgs field, an invisible ocean of energy that gives particles their mass. Right now, this field exists in what scientists call a false vacuum, a state that looks stable but is actually metastable, like a pencil balanced on its tip. The terrifying possibility, a quantum fluctuation or an extreme high-energy event, could nudge the Higgs field into a lower energy state, creating a bubble of true vacuum. Inside that bubble, the rules of physics would be unrecognizable. Atoms might disintegrate, forces like electromagnetism could cease to exist, and the universe as we know it would blink out like a candle in a hurricane. Here's where it gets even more unsettling. Once this bubble forms, it would expand in all directions, its walls racing outward faster than any signal could warn us. One moment, Earth would be here, the next, swallowed by a frontier where chemistry, light, even causality itself no longer function. The transition wouldn't just destroy life, it would erase the very conditions that allow matter to exist. And because it moves at light speed, we'd never see it coming. How close are we to this cosmic brink? Current particle physics suggests the Higgs field might be hovering just above instability, like a boulder on a mountainside held by a few pebbles. The Large Hadron Collider's measurements hint that we could be living in a universe teetering on the edge, a place where, given enough time or the right trigger, everything resets. Some theories even propose that vacuum decay could already be happening somewhere in the cosmos, with that deadly bubble hurtling toward us right now. Yet there's a twist that makes this horror story strangely beautiful. If vacuum decay occurred, it wouldn't just be an end. It could be the birth of a new universe with entirely different physical laws. The shockwave might forge a fresh cosmos in its wake, one where new forms of matter, energy, or even life could arise under rules we can't begin to imagine. The chilling truth, we may never know if we're standing on solid ground or thin ice until it's too late. But in facing this existential risk head-on, science does something remarkable. It transforms fear into understanding. Vacuum decay isn't just a doomsday scenario. It's a reminder that stability itself might be an illusion, and that the universe in all its splendor is far more dynamic and far more dangerous than it appears. Brain cosmology turns the universe inside out, literally. Imagine our entire cosmos isn't floating in empty space, but trapped on the surface of a vast, rippling membrane, like a water strider skimming a pond's surface. This isn't just a poetic analogy, it's a radical reimagining of reality rooted in string theory's most audacious idea, that our universe might be a three-dimensional brain existing within a higher dimensional realm called the bulk. And here's the mind-bending twist: the expansion of space we've been measuring could be driven by forces leaking into our brain from these hidden dimensions, like shadows cast by giants we can't see. The Randall-Sundrum models proposed in the late 1990s gave this wild concept mathematical teeth. They showed how gravity, the force we thought we understood, might actually be diluted by spilling into extra dimensions, explaining why it's so weak compared to other forces. Picture a campfire's heat. Stand too close and it's intense, but step back and it fades. In brain cosmology, gravity's strength dissipates as it spreads into the bulk, leaving only a faint echo in our universe. Meanwhile, particles like photons and electrons remain trapped on our brain, confined by unseen forces that shape their behavior. But how does this connect to cosmic expansion? A collision or vibration of brains in the bulk could inject energy into our universe, fueling the acceleration we attribute to dark energy. Imagine two sheets of paper floating parallel to each other. When they ripple and touch, the contact point releases energy, a cosmic spark that might have ignited the Big Bang itself. Some theories even suggest that dark energy's mysterious constancy could arise from the steady pull of a neighboring brain, forever hovering just out of reach in higher dimensional space. Evidence for this invisible architecture is scarce but tantalizing. If gravity does leak into the bulk, particle colliders might spot missing energy in high-speed collisions, a ghostly hint of particles escaping our brain. Others hunt for microscopic black holes that could form if extra dimensions exist at certain scales. And then there's the cosmic microwave background. Subtle anomalies in its patterns might carry imprints of brain interactions from the universe's earliest moments. Brain cosmology doesn't just reshape space, it redefines existence. If true, our universe is no longer the main stage, but a single act in a multidimensional drama playing out in realms beyond perception. The expansion we measure, the forces we take for granted, even the laws of physics themselves might all be local bylaws, quirks of our particular brain's position in a reality far vaster than we've dared to dream. Roger Penrose's conformal cyclic cosmology is the kind of idea that makes physicists both gasp and groan, a vision of eternity so elegant it borders on heresy. Imagine a universe that never truly ends. Instead, after expanding into near nothingness over trillions of years, it sheds all sense of scale and time, resetting itself into a brand new Big Bang. No collapse, no crunch, just a cosmic metamorphosis where the old universe's ashes become the next one's building blocks. This isn't science fiction, it's a daring mathematical rebranding of reality itself, where infinity hides in plain sight. The key lies in a sleight of hand called conformal rescaling, a way to mathematically stretch and compress the universe's dimensions without losing its essential shape. Picture a balloon deflating until it's a limp, featureless rag. Now imagine magically reinflating it, not by adding air, but by redefining what size even means. In Penrose's model, as the universe expands, particles lose mass, distances blur, and temperatures even out until all that's left is a smooth, uniform void. At this point, the dying cosmos becomes mathematically identical to the high-energy singularity of a new Big Bang. The cycle resets not by reversing time, but by erasing the very concept of scale. But how could we ever prove something so abstract? Enter Hawking Point's ghostly imprints in the cosmic microwave background that Penrose claims are the smoking guns of past universes. These faint, circular patterns of polarized light, he argues, are the scars of supermassive black holes from previous cosmic cycles, as those black holes evaporated via Hawking radiation in the eons before the reset. Their energy left faint bruises on the fabric of the next universe, like shadows of ancient titans lingering in the newborn cosmos's first light. Critics, of course, pounce on the theory's unproven leaps. The Hawking points Penrose identifies could just as easily be random fluctuations in the microwave background's noise. And conformal rescaling relies on assumptions about particle physics that remain untested, like electrons and protons eventually becoming massless as the universe ages. Even Penrose admits his model requires rewriting quantum field theory to eliminate the concept of mass at the reset point, a move that makes many physicists balk. Yet the theory's audacity is its greatest strength. Unlike models relying on dark energy or extra dimensions, conformal cyclic cosmology offers a starkly minimalist vision. the universe doesn't need mysterious substances or hidden worlds to be eternal. It just needs to forget itself periodically, like a phoenix that doesn't burn to ash but to pure geometry. Whether Penrose's circles are real or mirages, his idea forces us to confront a staggering possibility that the cosmos isn't just expanding but remembering. And if he's right, the night sky isn't just a window to space but to time itself, layered with echoes of universes we'll never see, but whose fingerprints might already be in our hands. What if space-time isn't the stage of the universe but the show itself? This is the startling premise of emergent space-time, a theory that flips our understanding of reality on its head. Instead of treating space and time as fundamental building blocks, like the canvas on which everything else is painted, this idea suggests they arise from something deeper, the tangled web of quantum entanglement. Picture reality as a cosmic illusion, a hologram projected from the frantic interactions of countless quantum bits dancing beneath the surface. The roots of this theory stretch back to the black hole information paradox, where physicists realized that everything falling into a black hole, every atom, every photon, leaves a kind of fingerprint on the event horizon, encoded in quantum entanglement. This hinted at something radical, entanglement, that bizarre, spooky action at a distance Einstein hated, might be stitching space-time itself together at the tiniest scales. Fast forward to today, and experiments with quantum computers and simulations of spin networks, abstract webs of interconnected quantum states, show that under the right conditions, entanglement can indeed generate something that looks and behaves like space and time. It's as if we've been staring at a mirage, mistaking the shimmer for water when the real magic was happening underground. Now connect this to cosmic expansion. If space-time emerges from quantum entanglement, then the universe's accelerating growth could reflect shifts in how information is shared across this hidden quantum network. Think of it like a social media algorithm suddenly amplifying certain connections, except here, the connections are the very threads holding space together. Some models suggest dark energy might be the cosmic equivalent of network lag, a growing disconnect in quantum correlations as the universe becomes too vast for information to flow smoothly. Others propose that expansion is the universe forgetting its quantum links, like a hard drive slowly corrupting, leaving gaps that stretch into what we perceive as accelerating space. Recent breakthroughs add fuel to the fire. Experiments with entangled particles in lab settings have shown that certain geometric properties of space-time, like distance and curvature, can be mathematically reconstructed purely from entanglement patterns. And in simulations using tensor networks, physicists have watched synthetic universes emerge from nothing but quantum connections, their virtual space-time expanding in ways eerily reminiscent of our own. Yet skeptics aren't convinced. If space-time emerges from entanglement, why does it seem so smooth and continuous at our scale? Why don't we see glitches or pixelation in the fabric of reality? Defenders argue that quantum effects average out at larger scales, like how individual grains of sand blend into a smooth dune. But until we can probe the Planck scale trillions of times smaller than an atom, the theory remains tantalizingly out of reach. The stakes are cosmic. If emergent spacetime is real, it means the universe isn't just expanding, it's evolving, rewriting its own operating system one quantum connection at a time. Dark energy, black holes, even the arrow of time might all be side effects of a deeper, weirder reality humming beneath the surface. And that's the most thrilling part. We might be standing at the edge of a paradigm shift, where the next great discovery isn't a new particle or force, but the realization that space and time themselves are cosmic sleight of hand. What if the universe isn't just expanding but rendering? This is the spine-tingling premise of simulation theory, the idea that our entire cosmos might be an unfathomably advanced computer program, with dark energy acting as nothing more than a line of code dictating the rate of expansion. Think of it like this: when a game designer builds a virtual world, they define its rules: gravity, light speed, even the way objects drift apart over time. Could the accelerating universe simply be following its programmed parameters, ticking forward like clockwork in some higher dimensional server? The argument starts with eerie mathematical perfection. Our universe's constants, the strength of gravity, the speed of light, the charge of an electron, are fine-tuned with a precision that defies randomness. Alter any one by a fraction and stars wouldn't ignite, atoms wouldn't bond, and life would never arise. It's as if reality were coded by a programmer who dialed in the values just right. Even the way quantum particles behave, snapping between states only when observed, mirrors how video games optimize processing power, rendering details only when a player looks at them. Then there's the Fermi paradox. If the universe is teeming with potential for life, where is everyone? Simulation theory offers a chilling answer. Advanced civilizations might have figured out the truth, that they're living in a simulation, and hacked their way out, leaving behind empty galaxies like abandoned game servers. Or worse, the simulation could be designed to keep civilizations isolated, a cosmic firewall preventing subjects from comparing notes across the universe. But here's the twist that ties it all back to dark energy. In a simulated universe, accelerating expansion wouldn't need a physical cause like dark energy. It could just be the program's way of managing memory, increasing the distance between galaxies to reduce computational load, like a computer lowering render quality for distant objects. This would explain why expansion's acceleration is so uniform, so eerily precise. No messy physics required, just efficient coding. Supporters point to glitches that could betray the simulation, like anomalies in high-energy particle collisions or patterns in cosmic background radiation resembling pixelation. Detractors argue that invoking a simulator explains nothing. It just kicks the can up the cosmic ladder to whoever built the simulation. But whether it's poetry or physics, the theory forces us to confront a haunting possibility. The universe's greatest mystery might not be why it's expanding, but who pressed play. Dark matter has always played the silent giant of the cosmos, an invisible scaffold shaping galaxies with its gravitational might. But what if its role in cosmic expansion goes far beyond just pulling matter together? Some theorists are now exploring a radical twist. Dark matter might not be the universe's anchor, but its hidden accelerator, subtly fueling the very expansion it was thought to resist. At first glance, the idea seems contradictory. Dark matter's gravity binds galaxies into clusters and slows the universe's growth, acting as cosmic glue against dark energy's relentless push. But dig deeper and the story gets murkier. Certain models suggest dark matter could decay over time, transforming into lighter particles or even into dark energy itself. Imagine an ice cube slowly melting into water, except here, the water is a repulsive force that stretches space-time. If even a fraction of dark matter were undergoing this metamorphosis, it could tip the scales of cosmic expansion, adding to dark energy's push in ways we've only begun to calculate. Then there's the possibility of dark matter interacting with dark energy through hidden forces, like two invisible actors on a stage we can't see. Some theories propose a fifth force that operates solely between dark sector particles, creating feedback loops where dark matter's distribution influences dark energy's strength. Picture a cosmic seesaw. As dark matter clumps in certain regions, it might amplify or dampen dark energy's effects locally, creating pockets of space where expansion surges or stalls. This could explain oddities like the Hubble tension, the stubborn discrepancy in measurements of the universe's expansion rate, if dark matter's behavior isn't uniform across the cosmos. The most daring ideas go even further. What if dark matter isn't a single substance at all, but a family of particles with split personalities? Some could be stable, anchoring galaxies, while others decay into exotic radiation that nudges expansion forward. Others might briefly wake up to interact with dark energy before fading back into obscurity. These scenarios aren't just flights of fancy, they leave fingerprints. If dark matter decays, telescopes might catch the faint glow of its remnants. If it interacts, we could spot distortions in the way galaxies bend light, subtle warps that reveal unseen forces at work. Yet for all its intrigue, this reshuffling of dark matter's role raises thorny questions. If it's decaying, why haven't we seen the debris? If it's interacting, why does its gravitational grip still dominate in galaxy clusters? The answers might lie in the next generation of experiments, underground detectors hunting for dark matter's whispers, or space telescopes mapping the universe's growth with razor-sharp precision. Until then, one thing's clear: the invisible bulk of our cosmos might be more restless, more dynamic than we ever imagined. Dark matter isn't just a passive backdrop to the universe's drama. It could be a lead actor quietly rewriting the script of cosmic expansion from the shadows. Somewhere in the depths of space, the universe might be keeping a secret, a hidden directionality, a cosmic bias that defies everything we thought we knew. Astronomers call it the axis of evil, a name that sounds ripped from a sci-fi thriller but refers to one of the most perplexing anomalies in modern cosmology. It all started when researchers noticed something unsettling about the cosmic microwave background, the oldest light in existence. Rather than being perfectly uniform, this fossilized glow seems to have a faint but unmistakable alignment, as if the entire cosmos is tilting slightly in one direction, like a table with one leg shorter than the others. The implications are staggering. The standard model of cosmology assumes the universe is isotropic, meaning it looks the same in all directions. The Big Bang should have blasted matter and energy outward with no preferred axis, like an explosion in a featureless void. But the axis of evil suggests otherwise. Measurements show that fluctuations in the microwave background, those tiny ripples that seeded galaxies, appear to line up along a specific plane, almost as if the universe has a north and south pole. Even more bizarre, this axis eerily aligns with our solar system's orientation, raising eyebrows about whether we're seeing a real cosmic signal or some strange observational bias. Could this be a glitch in the data? Skeptics argue the anomaly might stem from something as mundane as dust in our own galaxy contaminating the measurements, or subtle errors in how we've processed the microwave background maps. Others point out that with trillions of data points, statistical flukes are inevitable, like finding a face in a bowl of spaghetti. But the more we study it, the harder it becomes to dismiss. Independent analyzers using different telescopes and techniques keep finding hints of this directional oddity, piling up like breadcrumbs leading to a forbidden door. If it's real, the axis of evil could rewrite physics. One radical explanation invokes pre-Big Bang relics, ancient structures or fields that survived from a previous cosmic cycle, imprinting their influence on our universe like scars from a forgotten war. Another theory suggests we're seeing the gravitational tug of a neighboring universe beyond our cosmic horizon, warping space-time like a hand pressing against a curtain. The wildest idea, that dark energy itself isn't uniform but flows in currents, stronger in some directions than others, stretching space unevenly like taffy pulled at an angle. The name Axis of Evil might sound melodramatic, but it reflects just how disruptive this anomaly could be. Either we're staring at a cosmic coincidence so unlikely it borders on absurdity, or we've stumbled onto evidence that the universe isn't playing by the rules we've written for it. And that's the heart of the mystery, whether this axis is a mirage or a landmark. It forces us to confront the humbling truth that the cosmos might still have secrets no equation has yet cracked. At the tiniest scales imaginable, far smaller than atoms, smaller even than the particles that make them up, the universe is anything but calm. Empty space crackles with quantum fluctuations, a chaotic froth of virtual particles popping in and out of existence like bubbles in a boiling pot. These momentary fluctuations might seem insignificant, but they hold the key to one of cosmology's most profound revelations. The large-scale structure of the universe, from the distribution of galaxies to the accelerating expansion of space itself, might be written in the random whispers of quantum noise from the first moments after the Big Bang. Picture the infant universe, a searing hot soup of energy so dense that quantum effects ruled everything. According to inflationary theory, during this period, space expanded faster than light itself, but not perfectly smoothly. Quantum fluctuations introduced tiny irregularities, microscopic hills and valleys in the fabric of spacetime. As inflation stretched the universe exponentially, those minuscule wrinkles were blown up to cosmic proportions, like stretching a crumpled sheet of paper until its wrinkles become towering mountain ranges. Today, those ancient wrinkles are frozen into the cosmos as subtle variations in the density of matter, seeds that would eventually grow under gravity's pull into the galaxies and voids we observe. The evidence for this quantum origin story is etched into the cosmic microwave background, the afterglow of the Big Bang. The temperature variations we see in that ancient light aren't random. They follow a precise pattern predicted by quantum mechanics, with larger fluctuations corresponding to regions where matter would later clump together. It's as if the universe's blueprint was drawn by the probabilistic rules of quantum physics, with inflation acting as the magnifying glass that brought those hidden designs into view. But here's where it gets even more astonishing. These same quantum fluctuations didn't just shape matter, they might be driving the universe's expansion. Some theories propose that what we call dark energy could be a macroscopic echo of that primordial quantum froth, a residual energy embedded in spacetime itself. Imagine blowing up a balloon covered in tiny bumps as it inflates. The bumps stretch, but so does the rubber between them. In the cosmos, the rubber might be the vacuum energy left over from those early fluctuations, its repulsive push now accelerating galaxies apart. Critics argue this connection is speculative. Quantum effects are notoriously hard to pin down at cosmic scales, yet the math is compelling. When physicists calculate the energy density of quantum fluctuations in a vacuum, the numbers are absurdly large, enough to tear spacetime apart. The fact that our universe's expansion is accelerating at a much gentler rate suggests some mysterious cancellation or suppression mechanism is at work, like a cosmic pressure valve keeping reality stable. Whether this is coincidence or deep physics remains one of cosmology's greatest unsolved puzzles. What's undeniable is the eerie harmony between the very small and the very large. The same quantum rules that govern particles in a lab might have sculpted the cosmos itself, linking the fate of galaxies to the unpredictable dance of virtual particles. It's a humbling thought that the universe's grand design could owe its existence to randomness at the smallest scales, amplified by inflation into a canvas of stars, voids, and an expansion that shows no signs of slowing. In that sense, we're not just living in a universe shaped by quantum fluctuations, we're living inside one. The shape of the universe isn't just a cosmic curiosity, it could be the ultimate deciding factor in how this grand story ends. Imagine space itself as a sheet of paper, but is it perfectly flat, gently curved like a sphere, or warped like a saddle? This isn't just geometry, it's destiny. If the universe is closed with positive curvature like the surface of a globe, expansion could one day reverse, pulling everything back into a fiery collapse. If it's open with negative curvature like a twisting saddle, space might stretch forever into icy darkness. And if it's perfectly flat, as most measurements suggest, the scales could remain balanced between expansion and gravity, a cosmic tightrope walk with no net to catch us. The hunt for the universe's shape hinges on the cosmic microwave background, that ancient light frozen in time just 400,000 years after the Big Bang. Tiny temperature fluctuations in this relic radiation aren't just random noise, they're a cosmic fingerprint, encoding secrets about space's curvature. Picture the CMB as a hall of mirrors. In a closed universe, light beams would eventually loop back on themselves, creating repeating patterns like a room lined with facing mirrors. In an open universe, those beams would diverge endlessly, leaving ghostly gaps in the microwave sky. The fact that we see neither, just a near-perfectly uniform distribution, suggests space is flat to an almost eerie precision, within a margin of error of just 0.4%. But here's where it gets strange. A perfectly flat universe on observable scales doesn't necessarily mean space goes on forever. It could still be finite, wrapped in an intricate topology we can't yet perceive, like a video game world where stepping off one edge teleports you to the other. Some theorists propose the universe might be shaped like a donut or a kaleidoscope of twisted cubes, with hidden folds that light has traversed multiple times without us realizing. If true, we might spot matching circles in the CMB identical patterns on opposite sides of the sky, like cosmic déjà vu. So far, searches have come up empty, but the possibility lingers, a ghost in the data. Then there's the dark energy wildcard. Even if space is flat now, could curvature be hiding in plain sight, masked by dark energy's dominance? Some models suggest that early inflation might have stretched the universe so violently that any primordial curvature became vanishingly faint, like smoothing a crinkled sheet under a steamroller. But like a stretched rubber band, space might still carry tension, a memory of its original shape waiting to snap back. Future telescopes measuring the bending of light from distant supernova or quasars could reveal subtle warps hidden beneath the illusion of flatness. The stakes couldn't be higher. A closed universe guarantees a dramatic finale, a big crunch where galaxies rush together like moths to a flame. An open one resigns us to eternal expansion, a slow fade into oblivion. And a flat cosmos, it's the ultimate cliffhanger, balanced on a knife's edge between fire and ice, its fate resting on forces we're still struggling to name. The universe's shape isn't just a question of aesthetics, it's a matter of life and death, written in the geometry of emptiness itself. Every photon from the cosmic microwave background is a messenger from the dawn of time, whispering clues we're only beginning to decipher. And somewhere in that static, the answer waits not just to how the universe is shaped, but to how it will end. Time might feel like the most constant force in the universe, always flowing forward, never bending backward, but what if expansion itself is secretly unraveling it? Imagine a cosmic hourglass where the sand isn't just running out, but the glass itself is stretching so thin that the very concept of seconds loses all meaning. This is the chilling possibility lurking in some quantum gravity models, where space-time isn't a smooth, unbroken fabric, but a patchwork of discrete fragments like pixels on a screen. And as the universe expands, those pixels could stretch farther apart until time, as we know it, simply stops ticking. The idea hinges on a radical rethinking of reality's building blocks. In theories like loop quantum gravity, spacetime isn't continuous but granular, made of tiny quanta so small that 1 million of them could fit across a single proton. Normally, these grains stitch together seamlessly, creating the illusion of a flowing, unified cosmos. But in an eternally expanding universe, dark energy's relentless push could pull these threads too thin, stretching the connections between quantum pixels until causality itself starts glitching. Picture an old film reel played at extreme slow motion. The frames freeze, the story stutters, and eventually the movie stops altogether. Here's where it gets even stranger. Without time, there's no change, no decay, no events, just an endless static snapshot. Black holes wouldn't evaporate, particles wouldn't collide, and even entropy, the universe's relentless drive toward disorder, would hit a wall. It's not that everything freezes in place, it's that place, and when cease to have any relationship at all. The cosmos would become a fossil, perfectly preserved but utterly lifeless, like a butterfly trapped in amber the size of infinity. Some models suggest this dissolution wouldn't happen uniformly. Time might fray first at the edges of the observable universe, where expansion's effects are strongest, creeping inward like a wave of silence. Civilizations near the end would witness stars not just fading, but freezing mid-explosion, their light stretched into infinite red hues before vanishing into timelessness. By the time the phenomenon reached us, there'd be no us left to notice. Consciousness relies on time's flow, so its end would erase observation itself. Critics argue this scenario relies on untested physics. Quantum gravity remains one of science's greatest unsolved puzzles, but the math hints at eerie possibilities. If spacetime is indeed discrete, then expansion could push it past a breaking point, like a stretched rubber band snapping at the atomic level. And once time shatters, there's no putting it back together. No clocks, no causes, no futures waiting to unfold, just a universe that isn't dead or alive, but simply done. Whether this fate awaits us or not, the theory forces a humbling realization: time might not be universal. It could be a local phenomenon, a quirk of our cosmic neighborhood that fades with distance or entropy or dark energy's whim. The expansion we measure isn't just carrying galaxies away, it might be quietly erasing the stage on which existence performs. And if that's true, then every second that passes is both a gift and a countdown, not to an ending, but to the dissolution of endings themselves. Black holes have long been the ultimate cosmic paradox, regions where gravity is so intense that not even light can escape, where the laws of physics as we know them seem to break down. But perhaps their most baffling feature is what they do to information. According to quantum mechanics, information, the fundamental blueprint of every particle state, can never truly be destroyed. Yet black holes appear to erase it completely, swallowing stars, planets, and light, leaving behind only mass, charge, and spin. This contradiction, known as the information paradox, has haunted physicists for decades. Now, some theorists are asking an even more radical question. Could the same forces that scramble information inside black holes also be shaping the universe's expansion? At the heart of this idea lies entropy, the measure of disorder in a system. Black holes aren't just cosmic vacuums, they're entropy powerhouses with their event horizons acting as membranes that trap unimaginable amounts of quantum information. Stephen Hawking stunned the world when he showed that black holes slowly leak radiation and eventually evaporate, seemingly taking all that trapped information with them. But if information can't vanish, where does it go? One possibility is that it's encoded in the Hawking radiation itself, scrambled beyond recognition like a shattered mirror reflecting a distorted world. Now zoom out to the cosmic scale. The universe too has an entropy budget, a limit on how much disorder it can contain. As space expands, that capacity grows, but so does the total entropy driven by star formation, black hole collisions, and the relentless pull of dark energy. Some scientists propose that the universe's expansion might be constrained by these information limits, like a computer struggling to render an ever-expanding virtual world without overloading its memory. Just as a black hole's event horizon sets a boundary for how much information it can hold, the cosmic horizon, the farthest distance light could have traveled since the Big Bang, might act as a cap on universal entropy, subtly influencing how fast space can stretch. The implications are staggering. If information preservation shapes cosmic expansion, then dark energy's acceleration could be a reflection of the universe, making room for new entropy, like a librarian endlessly adding shelves to hold an ever-growing collection of books. Alternatively, the expansion might slow in regions where information density becomes too high, like a traffic jam in the fabric of spacetime. Some models even suggest that the universe could hit an information saturation point, a moment when entropy maxes out, triggering a phase transition as profound as the Big Bang itself. Critics argue these ideas are speculative, leaning heavily on untested quantum gravity theories. Yet the parallels are hard to ignore. Black holes and the universe both have horizons. Both deal in entropy, both seem to play by rules we don't yet understand. Whether this connection is coincidence or cosmic truth remains to be seen, but one thing is clear: the fate of information, and perhaps the universe itself, might hinge on answers we're only beginning to glimpse. The paradox that started with black holes could end up rewriting everything we know about existence. Infinity is a dangerous idea, not just because it stretches the mind, but because it introduces possibilities so bizarre they border on nightmare fuel. Enter the Boltzmann brain, a thought experiment that turns cosmic expansion into a philosophical house of mirrors. Imagine a universe that exists for eternity, where particles randomly collide over and over across infinite time. Given enough chances, even the most improbable events become inevitable, including the spontaneous formation of a fully self-aware consciousness, complete with fabricated memories of a life that never happened. This isn't sci-fi, it's a direct consequence of statistical mechanics, and it forces us to confront a chilling question. If the universe keeps expanding forever, are we the unlikely real minds, or just fleeting fluctuations in an ocean of chaos? The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who first grappled with the statistical nature of entropy. In an infinite, eternally expanding cosmos, even highly ordered states, like a functioning brain, can occasionally arise from random particle collisions, like shaking a box of Scrabble tiles until they spell war and peace. These Boltzmann brains wouldn't emerge from evolution or biology, but from pure thermodynamics, fully formed and convinced of their own reality. The terrifying implication: given enough time, Boltzmann brains would vastly outnumber real observers like us, making it statistically more likely that you are one of these momentary aberrations, hallucinating the entire universe right now, than an authentic product of billions of years of cosmic history. Physics hasn't been kind to this idea, and for good reason. A universe dominated by Boltzmann brains would render science meaningless, since any measurement or memory could be an illusion. But here's the twist: cosmic expansion might actually prevent their formation. For a Boltzmann brain to materialize, the universe would need regions where particles could still interact freely, despite dark energy's relentless stretching. Yet if expansion accelerates indefinitely, space will eventually become so vast and empty that particles lose all contact, freezing the cosmos into a state where even randomness can't assemble complexity. The irony: dark energy, often cast as the villain of cosmology, might be the very force that preserves our sanity, keeping reality too sparse for existential paradoxes to take root. But the Boltzmann brain dilemma isn't just about physics, it's a mirror held up to our deepest assumptions about reality. If we dismiss these phantom minds as absurd, we're implicitly trusting that the universe follows rules beyond raw statistics, some deeper order that favors structured evolution over random chance. That trust is the bedrock of science itself, yet the fact that Boltzmann brains are even possible hints at something profound. Infinity doesn't just stretch space and time, it warps logic, turning the improbable into the inevitable. Whether we're real or statistical mirages might be a question cosmology can't answer, but the mere act of asking it reveals how fragile our grip on reality might truly be. The universe might not just exist, it might require us to witness it into being. This is the spine-tingling premise of the participatory universe theory, where consciousness isn't a passive byproduct of cosmic evolution, but an active architect shaping reality itself. At the heart of this idea lies a quantum riddle. Particles seem to behave differently when observed, as if the mere act of measurement forces them to choose a definite state. Now stretch that quantum weirdness across the cosmos. Could the universe's expansion, the very fabric of spacetime, be subtly nudged by the collective gaze of conscious observers? John Wheeler, the visionary physicist who coined the term black hole, dared to explore this possibility with his infamous delayed choice experiment. Picture a photon racing toward a screen after passing through a beam splitter. a device that lets it travel two paths at once. Normally, the photon acts like a wave, creating an interference pattern. But if you place a detector to observe which path it takes, the photon abruptly decides to act like a particle, as if rewinding time to change its behavior based on your future observation. Wheeler's twist: you can wait until after the photon has already traveled its path before choosing whether to measure it, and somehow, the photon still adjusts its past actions retroactively. It's as if reality holds off committing to a version of events until a conscious observer steps in to cast the deciding vote. Now, scale this up to cosmic proportions. If quantum systems remain in flux until observed, could the universe itself be in a superposition of possibilities, expanding faster here, slower there, until conscious life emerges to collapse it into a specific trajectory? Some interpretations suggest that dark energy's acceleration might not be a fixed law, but a dynamic response to the growing web of observation woven by sentient beings across galaxies. Imagine consciousness as a cosmic tuning fork, resonating with the quantum underpinnings of space-time and subtly harmonizing the rate of expansion. Critics dismiss this as metaphysical speculation, arguing that observation in quantum mechanics simply means interaction with any macroscopic system, not literal human awareness. Yet the deeper you dig, the harder it becomes to untangle observation from the observer. In quantum field theory, vacuum fluctuations, the seething energy of empty space depend on boundary conditions, almost as if the universe checks its surroundings before settling on an energy state. Could those boundaries include the presence of conscious entities? The implications are dizzying. If consciousness influences cosmic expansion, then the universe isn't just hospitable to life, it might be tailored by it. Dark energy's eerily fine-tuned value, the improbable flatness of space, even the arrow of time could reflect a feedback loop between mind and matter. It's a vision of reality where we're not just passengers on a runaway cosmic train, but co-engineers laying the tracks as we go. Whether poetry or physics, the participatory universe forces us to confront a humbling truth. The cosmos might not just be unfolding around us, it might be unfolding because of us. Imagine if the universe wasn't just described by mathematics, but was mathematics, not a physical thing governed by equations, but an equation itself, unfolding like a cosmic calculation where every galaxy, every particle, and even the expansion of space are just numerical expressions in an infinite formula. This is the brain-melting premise of the mathematical universe hypothesis, championed by physicist Max Tegmark. In this view, reality isn't made of matter or energy, but of pure, abstract mathematical structures and the accelerating expansion we observe. Just another line in the cosmic code, an inevitable output of the algorithm we call existence. Tegmark's argument starts with an observation so simple it's often overlooked. Every physical theory, from Newton's gravity to quantum mechanics, is ultimately a mathematical model. The uncanny precision of these models, how a handful of equations can predict everything from the orbit of Pluto to the glow of distant quasars, suggests something profound. Math isn't just a tool we use to understand the universe. It might be the universe with physicality as an emergent illusion. Think of it like a video game. The worlds you explore aren't made of pixels, but of the underlying logic that generates them. In the same way, stars and galaxies might just be shadows cast by deeper mathematical truths. Now apply this to cosmic expansion. If the universe is math, then dark energy isn't a mysterious substance, it's a parameter in the equation, a fixed value in the cosmic program determining how fast space stretches. The eerie fine-tuning of this value, perfectly balanced to allow galaxies and life, suddenly makes sense. In a purely mathematical reality, all possible structures exist somewhere in the multiverse of math, and we find ourselves in one where the parameters permit consciousness not because of luck, but because self-aware substructures only arise in certain computational branches. Critics, of course, push back hard. If the universe is math, why does it feel so tangible? Why do we experience warmth, color, and pain instead of just cold equations? Tegmark counters that these qualia might be inevitable patterns in information processing, like how the number 7 evokes different associations but remains fundamentally abstract. Others argue the hypothesis is untestable. If every conceivable mathematical structure exists, how do we distinguish our universe from the rest? Supporters retort that testability lies in the simplicity of the underlying math. The equations governing our cosmos might be uniquely elegant, a signature we could one day identify in the fabric of spacetime itself, the most staggering implication. If Tegmark is right, the universe's expansion isn't something happening to space, it's space itself being computed, frame by frame, in a cosmic arithmetic we're only beginning to decode. Whether this is profound truth or philosophical sleight of hand, it forces us to confront a haunting possibility. The ultimate nature of reality might not be energy or strings or even information, but numbers dancing in the void. And if that's true, then every galaxy racing away from us is just another digit in the greatest equation ever written. From phantom energy stretching reality to shreds, to black holes birthing entire universes in their depths, we've ventured through a labyrinth of possibilities where each turn reveals something stranger than the last. The sheer diversity of theories about cosmic expansion isn't just a testament to human curiosity, it's a mirror reflecting how little we truly grasp. Dark energy, quantum fluctuations, higher dimensional brains, each idea is a flickering candle in the vast dark, illuminating fragments of a puzzle we're only beginning to assemble. What's striking isn't just the range of explanations, but how alive the debate remains. Even now, new data from telescopes like Euclid and JWST could upend everything overnight, turning today's leading theories into tomorrow's footnotes. Maybe dark energy is Einstein's cosmological constant, or perhaps it's something far weirder, a force that evolves, flickers, or even talks back to the fabric of spacetime. The multiverse, the holographic principle, time's eventual dissolution, these aren't just sci-fi plot twists. They're real, viable hypotheses fighting for oxygen in the cutting-edge journals of cosmology. And that's the beauty of it. The universe refuses to be pinned down. For every elegant equation, there's an anomaly that doesn't fit. For every observation, a dozen interpretations. The axis of evil, the Hubble tension, the vacuum catastrophe, these aren't just hurdles. They're invitations, clues that the cosmos is hiding layers we've barely scratched. So here's the real question: which of these wild ideas resonates with you? Do you think we're hurtling toward a big rip or trapped in a cosmic simulation? Maybe you're convinced gravity itself is a cosmic illusion, or that another universe is brushing against ours in the dark. Drop your favorite theory in the comments, because the greatest mystery isn't just out there. It's in the conversation, the collective wonder, the shared thrill of not knowing. And if you're hungry for more deep dives into the unknown, hit subscribe. The universe isn't done surprising us, and neither are we.